So good afternoon, and I am back with a lab report, and this one here deals with observing wavelengths. And so in order to complete this experiment, I have some water here. I also have a flat container with a ruler attached to it to better assist with observing. I have a smaller ruler to measure the depth of the water in the container, and I have a stopwatch that I can use to measure the time in seconds that I will be using on this experiment. Alright, so the first instruction is to fill the container with about 2 cm of water. So which is what I'm doing now. Alright, so we will take the measurement of the water. It is approximately nearly 2 cm, almost 2 cm of water here. Alright, so now that I've filled the container with water, I will tap the surface once every second. So I'm going to start my timer. Alright, so alright, so the next instruction now is to tap the water on a much faster level. So let's go. Alright, so what have we learned so far? We know that water waves are transverse waves due to energy being transferred across the x-axis. That's from right to left or left to right. And what we see so far is that the energy in this case, in this experiment, was the tapping of the water periodically, first at intervals of 1 second and then intervals that were even faster. So the first question asked is, how is the spacing of the water waves related to their wavelength? So let's say, for example, that we have a horizontal plane here, or the water is level, and we begin to have some waves. Alright, so what we see here are some waves, and from this point at the top to the other point is what we call the crest at the top there. So from one crest to the other is what we call a wavelength, and we can also call it the water wave. Reason being, that is what we will see at the surface of the water. Now the wavelength can also be from this part here to this other part where we have that complete what we call oscillation or a cycle. That is also what we call a wavelength. So what is the relation there? The spacing of the water and the wavelength, they are the same thing. Let us now discuss the question: how does the spacing of the water waves change when the rate of tapping increases? The first point to note here is that lower frequency means longer wavelengths. Now we're going to take a look at the wavelengths at 1 tap per second, and you can see here in the zoomed area the number of waves in a particular space. Now you can see that they are much more relaxed, they are longer, and this is at 1 tap per second. So we conclude that when you are tapping at 1 tap per second, you can see the wavelengths, they are long. Next point we have is that increased frequency or much more energy input, all right, means shorter wavelengths. So if the frequency is doubled, all right, you're now tapping at 2 times per second, that means that the length of the waves will be half the length that they were in the previous diagram. Now take a look at this here. Wavelengths at more than 1 tap per second. Now you can observe here that in the same space that they had a few waves in the first diagram, we now see that there are much more waves in this here. They are not as relaxed and long as the first diagram. There are now many more waves in the same amount of space. And so what is the relation between the increase of tapping and the water waves? What is the relation there? We come to the conclusion that the two, frequency and wavelengths, they are inversely related, meaning if one is increased, the other is decreased. If the frequency is lower, the wavelengths are longer. If the frequency is high, the wavelengths are shorter.